So this is the recording for the lesson from section 8.5. The recording that I made in class, the file got corrupted, so I wasn't able to upload it. So I am just going to walk through the notes that I posted, and hopefully this will help. So we did integration by partial fractions, and I started off by just reminding everybody how to add fractions with unlike denominators. So this first example is not at all partial fractions. So remember, you got to find a common denominator. In this example, this is the LCD. And so in the first fraction, to make this denominator look like the LCD, we'd have to multiply top and bottom by x plus 2. So that's why the 2 gets multiplied by x plus 2. And then in the second fraction, I'd have to multiply top and bottom by x minus 1. And so that's why you can see on the top, we have minus 4 times x minus 1. And it's all over the LCD. And then I just combined like terms from the numerator to get this. Now the point of me doing this problem is the method of partial fractions, before we get to integration, just partial fraction decomposition is taking a fraction that's already been combined and breaking it up into these pieces. And so we basically work backwards. The only problem is we can't just do these same steps backwards, because how would you know to take this numerator and break it up like this? And the answer is you don't know. So we have a different method for doing it. Instead, what we do is from the answer, we know what the breakdown is going to look like. You got an x minus 1 and an x plus 2 in your denominator, so we know we're going to have fractions with those denominators, so then the goal is going to be trying to find the numerators. So let's take this same problem, work with this single fraction and try to break it up, decompose it into these two fractions. And so that's what we did in this example. So we take the original, and like I said, we know that the denominator factors into these, so we know that the decomposition has to have each denominator as a fraction. And then you have to look at your numerators. Now your numerators, always consider them being 1 degree less than the factor in the denominator. So this has a degree of 1. Your numerator is going to be 1 degree less. It's going to be degree 0, so it's a constant. Same thing here. This is a degree 1. Your numerator is going to be degree 0. So you make an equation, and then what we're going to do is we're going to use the fact, look, if you look at this equation, there's 3 letters. There's an A, there's a B, there's an X. And these letters actually are doing 2 different roles. The A and the B represent constants. So these values don't change. But X does change. X can take on any value in this problem. So we're going to use that to our advantage. And the first thing, though, is we're going to make this a little easier to work with. So we're going to multiply through by the LCD. And so you multiply the first fraction by the LCD, and the x minus 1 and x plus 2 cancels. The entire denominator cancels, and you're just left with the numerator. When you take this LCD and multiply it by this fraction, this time the x minus 1's cancel, and you have a times x plus 2 left. And then the x plus 2's cancel, and you have b times x minus 1 left. So now we got this. And now what we're going to do is we're going to use that fact that x can be any value, but a and b will be fixed. And we're going to pick just any letter, any number we want, although there's some convenient values. And so anytime you have linear factors, let x equal what makes those factors equal 0, because then you get these really easy equations that you see down here. So negative 2 makes this equal 0. Let's let x equal that. So we'll put negative 2 in here for this x. This becomes 12. Negative 2 into this x makes this whole term turn into 0, which is why we don't have it. And then negative 2 minus 1 makes negative 3b. And once we know this, that means b is negative 4. So we found this numerator. Now 1 will make this equal 0, so let's let x equal 1. You put a 1 in for this x, you're going to get 6. Put a 1 in for this x, you're going to get 3a. Put a 1 in for this x, you get 0, so we don't even have it. Now we know a is 2. So now we substitute back in. A is 2, and b is negative 4, and that is exactly what we started with. So It works. Yay. So now that we kind of gotten the hang of partial fraction decomposition, let's just look at just the setup. For this section, the homework and anything I give you on the test, I'm going to keep the problems relatively simple. Nothing's going to get more complicated than what you see on the homework. So I don't know if you remember from last year, but partial fractions can get pretty icky. But I'm going to keep things relatively simple this year. But what if I asked you to set up the partial fraction decomposition for this? And so we have this denominator. The numerator actually is irrelevant when you're setting it up. But if you look at the denominator, we actually have some factors that have been repeated. This x cubed plus 4, since it's squared, that means that this factor gets repeated twice. And then this is x squared. It's like x times x. The x factor is getting repeated twice. Anytime you have repeated factors, you're going to need multiple denominators. And the rule for the repeated factors is you start off with the factor to the first power, and then you keep increasing the power until you get to what you got. So this was just x squared. So we start with x to the first power, x to the second power, and then we can stop there because that's what we had. If this was x cubed, we would need one more fraction with x cubed. So we'd have an x squared, x cubed. Then we need this fraction, or this factor in its denominator. And then this denominator is also repeated twice. So we have it to the first power, and then we raise it to the second power. So we actually have to break this up into 6 different fractions. Now I'm going to work backwards, just kind of go with it. But remember what I said above. The numerator, when you set up the numerator, it's always going to be 1 degree less than the factor in the denominator. So if you look at this denominator, the whole entire denominator would be x to the 6th. That would be degree 6. But that's not the factor. The individual factor in the denominator is just x cubed plus 4. That's degree 3. So the numerator is 1 degree less. Same thing here. This factor is degree 3. The numerator is 1 degree less. This denominator, the factor is degree 2. The numerator is 1 degree less. This one, remember, think of it like x times x. The individual factor is x, which is to the first power, degree 1. The numerator is degree 0. This is degree 1. The numerator is 0. So just to kind of remember how to set them up when they get more complicated. But like I said, I'm not going to give you anything. This would just be a nightmare to have to do by hand. I promise I won't make you do that. All right. It would actually be a nightmare to even just have to punch in all those things on a calculator. Ugh. So let's do some integration now. So let's take this problem. Now you can always spot when you're going to use partial fraction decomposition, because number 1, you have a rational expression, and number 2, your denominator factors. Use partial fraction decomposition. Decompose this and then try integrating. So the denominator is already factored for us. We're going to do the partial fraction decomposition. Remember, this is an x repeated twice, so it gets 2 different denominators, and then we have this fraction. And then that's the LCD. So I'm going to multiply through by the LCD. I multiply the first fraction, the entire denominator cancels out. We just have x minus 1. This fraction, the x cancels with one of these x's. I still have a times another x times x plus 1. With this fraction, the x squareds cancel, and we have b times x plus 1. And then with this one, the x plus 1's cancel, and we have c times x squared. Now remember what I said before. Anytime you got a linear denominator, let x equal whatever makes that equal 0. It'll be very easy to work with then. So we're going to take this equation, and I'm going to first go ahead and plug in 0, because it makes that denominator equal 0. So if I let this x equal 0, I get negative 1. X equals 0 makes this term go away and also this term, and I'm just left with b times 1, or just b. I know what b is. Now I can use this denominator. Negative 1 will make that equal 0. Negative 1 minus 1 is negative 2. Negative 1 will make all of this equals 0. And then we just have c times 1. So now we know what c is. But now we're out of values. We don't have any more denominators, any more different factors. So at this point, just pick some value for x. You can pick anything you want. We picked 1 because it was easy. I could have picked 17 if I wanted to. You pick whatever you want and plug it in. So if I let x equal 1, 1 minus 1 is 0. This term will become 2a. This term will become 2b. This term will become c. But we do know what b and c equal, so I can plug those in, and then I'm able to solve for a. And now I have all 3 numerators, and I just plugged in. And that's where I got this. A is 2, b was -1, and c was -2. So now I have this pink integral, and then it's a lot easier to integrate. So I go ahead and just integrate it now. Here's the integral of each term. I'm going to evaluate from 1 to 5. So I plugged in the 5, I plugged in the 1, and then I just worked on condensing it, and I got this. Remember when you're condensing, subtraction in between the logs means to divide the arguments. Multiplication means to multiply. So 5 divided by 6 would be 5/6. Times 2 would be 10/6, which is what reduces to 5/3. And that's it. So I went ahead and then gave these problems here. So I would encourage you to pause the video and go ahead and try these. Let me give you pause it right now if you just want to try it. Unfortunately, I left this hint up here already. But pause the video if you want, try them on your own. And then I'm going to just, in a second, I'll give you some hints on them in case you get stuck. Okay, so if you're back and you got stuck, this first problem, hopefully it looked familiar to you. It is the first example that we did. So we've already done the partial fraction decomposition. When you do that, it should be easy to integrate. So go ahead and do that. This one, you may have noticed, hey, the denominator doesn't factor. Remember what I said, if the denominator doesn't factor, you can't use partial fraction decomposition. So this is actually a problem we already learned how to do. It isn't as obvious though, but if you think about this formula here, this formula might be a little familiar to you. It should be. This was our arctan formula. So if you take a look at this problem, a good sign that you're going to use arctan, it's not a definite because it does, your numerator also matters, but if the denominator is the sum of 2 squares and this denominator is the sum of 2 squares. So see if you can remember how to do this problem using that. With number 6, the original problem isn't even rational. Trig does not make rational expressions. So this at first doesn't seem like partial fraction decomposition. But I do notice in the denominator that this does factor. And, like I got these cosines. I know the derivative of cosine is negative sine. I basically have that up here. I'm thinking I could let u equal cosine and do something with that. So that's my hint here. Let u equal cosine and see if you see what to do with it. All right, pause the video again, give it a shot. All right, here we go. Here's the first one, very straightforward. Like I said, we already did the PFD, so here's a partial fraction decomposition. We broke it up into this, and then these are just natural logs. And so there's the answer. Boom. I know one question some people might have is, wait, do I have to put my answer like this? Can I leave it like this? And the answer is, I don't know. I mean, really, there's no rule that says condensing is more simplified. It's just condensed. And so it really depends on what you're going to be doing with it afterwards. If this is going to be your final answer, then it really doesn't matter if you put your answer like this or like this. However, as you know with my tests, make sure you pay attention to the directions, because my directions may say something about condensing your answer or write it with only one natural log or something, because I want to make sure you remember how to condense. If it's multiple choice, it could be given condensed, so you should know how to get this. But if the problem doesn't give any indication how to leave your answer, really either form is fine. All right, let's look at the next one. Oh, oops, I have a blank page in there. So here was the next one. So like I said, the denominator doesn't factor, so we're going to use this formula instead. So if you rewrite this as 4x squared, then we see u is 4x squared, which means du is 8x dx. Now we're supposed to have du in the numerator, which we don't yet, but if I multiply by 8 and then divide by 8, I keep it equivalent, and now it's a perfect match. So I just literally plugged into the formula. Yay! So that's example 5, and then example 6. So first, this is just kind of explaining, hey, wait, it doesn't look rational, but blah, blah, blah. So actually here, let's start with the u substitution. So I gave you the hint of letting u equal cosine x. And remember, I picked that because that's what's going on in our denominator, and the derivative of cosine is up here. So I'm thinking I'll be able to do something with it. So if I let u equal cosine, then du is negative sine x dx. I have a sine x dx, just not the negative, so I put it over here. So sine x dx is negative du. And then if cosine is u, this becomes u plus u squared. So now I'm going to go ahead and scroll up. So this, now we can see this is rational and this denominator does factor. So now I can do partial fraction decomposition. Now some people in class are like, but wait, you don't have anything on the top, you have du. Can you do partial fraction decomposition on that? And the answer is yeah. Remember, I can just think of this as a 1 in the top and put the du off to the side. So that's why I'm really thinking of the fraction like this with a 1 in the numerator. So did partial fraction decomposition, and I got this. So just kind of follow the same steps we've been doing. Set it up, multiply by the LCD, let u equal what's going to make the factors equal 0, and you can find your values for a and b. Plug them in, and here is our new integrand. And so then I went ahead and integrated, and I distributed the negative here, and then I condensed, I substituted back in cosine, and then simplified the answer to write it without a fraction. And there we go. There's your final answer. And that was the end of the notes. That was all she wrote. So hopefully this helped. Sorry about the snafu with the video, and it took so long to get this up there. I will see you Friday in class. Bye-bye.